Okay, I forgot about that entirely. So this part of the lecture obviously is not going to be recorded, and I'm not going to go back and re-record that either, because I'm pretty sure some of you are saying, but Tech, this is what you do with the previous program, except the previous program was actually more complex because we have to test X, to see if it is greater than 2. This time we just want to see whether it's a 0 or not. All right. All right, so we are now going to test this code. Okay, it is far from complete, but we're going to test it. Okay, so we're going to test it. This is under the new tree subfolder. It's called struct.ttpsm. I think I could be wrong. Let me double check. Nope, it's tree. Okay, I was wrong. So this is actually tree.ttpsm. And I do have to say, with the script, it does make the job easier. And now we can go back to the assembler, go to the analysis tab, and we want to find out, what. So now I want to, kind of test you guys. Okay, how do I know whether the program worked or not? All right, so I got some comments from Paul. Constructing debugging the tree program using River Spider. I kept getting a message of wget. Oh, you need to use the updated version of the script because the trace itself is getting too long, and the way I was passing the trace to the script, to the remote script, didn't work when it is more than 4 kilobytes. That's why on one of the days I released a new version of River Spider that can handle longer traces and also longer programs. But I cannot remember which day it was. It was one of the days. I cannot remember which one. Oh, okay. Oh, okay. So you knew about that, but you didn't know whether the version that you're using is up to date or not. Okay, gotcha. Okay. Yeah, that's the problem of using multiple machines because I encountered the same kind of problems when I had multiple machines. So now I just consolidate everything on one single machine. And for those of you who, if you need to do something like this, and you want to consolidate, one option these days is to use a virtual machine, and you can run the virtual machine fairly effectively, depending on your setup, your computer setup. You can run it, you can run the virtual machine fairly effectively, even using an external hard drive. So that way you can install, whatever operating system you want in the virtual machine, and just take that external hard drive with you. And as long as there's a way to start up the virtual machine on a computer, hey, it's going to be the same setup. Okay, that's interesting. That's an interesting comment. All right, so getting back to this this program here. So how do I know whether the program worked or not? So let's go back to the source code and find out what the program should have done this time. So the program has not changed. I did not change main, which means we are not passing a null pointer this time. So because PTR is non-null, it should not be doing the JCI, and instead it should be going for the no op instruction. So we want to make sure that no op NOP is executes in the trace. And to know whether it executed or not, we can go to the Assemble tab, look for the no op, which is right here. Okay, so here's the no op instruction. It is at location 19. So now we go back to the trace analysis and see if 19 it executes or not. So we are quite sure that 19 did execute. And for those of you who are paranoid about, but we are not really sure, okay, well, then you want to check to see if the Z flag is a 0, at the end AA instruction, and the answer is yes. We did end up with the Z flag being 0, and that's why JZI did not branch, and instead it just kind of fell through to the no op instruction. All right, so the program did work. Okay, I retrieved the correct. Okay, so just knowing this doesn't mean that it retrieved the correct um, pointer. So we want to know whether f, 0f is indeed PTR itself. Okay, so that's the next thing we need to check. So for that, we have to look back to the C code because remember the assembly code is trying to mirror the C code. So in the C code, we are passing the address of A. Okay, and A is defined like this in the C code. In assembly code, it is defined over here, and this byte, which is representing the decimal value of 10, the address of this byte, which is the label A, is the address that we should find, and we are hoping that that is 0f, and we can check that. Okay, so the nice thing is we can check all of these things. So we now go all the way up to label A, which is here, and we can see label A is indeed the symbolic name of the address of 0f. So everything checks out. Okay, I did retrieve PTR as a parameter correctly. I did check whether it is 0 or not. Okay, I shouldn't claim that because I did not check the case when it was 0. So the next thing we might want to do is to change the parameter. When we pass A, as a parameter, we want to change it to 0, just to check whether that is going to work or not. And oh, that is the, okay, let me check the C code again. All right, so it is a pointer to a struct node, and it is the second thing that we passed. So in the assembly code, it is corresponding to whatever this A is, and this A is confusing because it looks like we are copying register A to register A, but that's not true because remember the second operand of LDI is always an immediate expression. In other words, it is referring to label A in this case. So if we want to test, okay, to see whether it can handle a null pointer correctly, then we'll change this to a 0, and then we rerun the trace to make sure that we skip the no op instruction this time because the JZI should branch because the Z flag should be set by the AND AA instruction. So I'm not going to do this. I'm just going to be okay. Just because this is the time when I have to say, it's really hard to practice what I tell you guys to do, and because the amount of time I can do this in the class is limited, so I cannot go through the entire process. But if I was actually doing this as a homework assignment, I would have tested it too because it doesn't take that much time, and it can rule out the possibility that the program doesn't know when to terminate, because one of the most frustrating thing about dealing with recursion is it does not stop. Okay, because recursion is a form of loop, so when it doesn't stop, then it becomes kind of problematic. So in real life, it would have been a good idea to put a 0 here to make sure that the subroutine does return correctly when the pointer is null. All right, so that is what I'm preaching to do, but I cannot do it here because I don't have enough time. All right, so now we're going to go in and actually implement what is inside here. So we need to check, now that we know that PTR is non-null, it is pointing to a structure somewhere in memory. The next thing we need to do is to check the L member of the structure that is pointed to by the pointer and see if that in return is null or not. All right, well, that's not too difficult. And you can also see how pointer is used kind of throughout this code here. So I'm not going to optimize the code because it will just kind of throw in a lot more confusion. So I'm just going to recompute everything, which is very tedious, and it uses up instruction space, but it doesn't hurt. Okay, so we're going to do it. We'll just forget that register A already has PTR in it. So the next thing we need to do is to load a different register with the offset to member L. So don't make assumptions, okay? Don't make the assumption that L is at 1 byte after the beginning of the node. Always refer to the symbolic name, which is already in the skeletal program. So always refer to the symbolic name, which is node_L. and then you want to add these two. Now, which way you want to add really does not matter, but I'm going to try my best to preserve PTR. So I'm adding PTR to the offset. So now register B has the address of L, remember L? So I'm gonna do a LD BB because I need to check whether that member itself is null or not. I'm not, because the address cannot be null. I just need to check whether the value is null or not. So now I'm going to do the same trick, and BB, okay, and then JZI to get around the inner loop. So now we have to be careful about the label names because now we have to say, which one are we talking about? So this is the embedded conditional statement. So I'm going to say then and if because it is the first nested conditional statement in the outer conditional statement. So I'm just going to use this name and then I'll put a label here, T, then, and if one, and put a semicolon here. Alright, so if L is not null, then we're going to do the recursive call. So the recursive call just needs to get array, and then that thing that we computed earlier, push both of those on the stack and then call traverse again. Alright, so array has never been touched, so we have to compute it. So I'm going to do LDI. This time I'm going to use register C because I know register A and B seem to be quite useful at this point, so I'm going to put it into register C because I do have register C available at this point. Okay, so I'm going to put the offset to array into register C, add CD so that we have the address of array in register C, LD CC, so we get to array itself, and then we push it on the stack. So we say decrement D stdc. So now we push array on the stack. Then we have to push ptr points to L, this thing here. This time I'm not going to recompute it because it's just way too much trouble to recompute it. So I'm just going to say, we still have it in register B, so we're going to use decrement D to allocate the space stdb to push the value of member L of the structure the PTR is pointing to. That's what's in B at this point. And now we can push the return address. So don't forget to push the return address. So we can put that into, register C is not going to be useful anymore. So we'll put in register C. .6 plus decrement D stdc. Alright, so we got all three useful things pushed on the stack right now, so we can do a JMPI to traverse. And when traverse comes back, we have two items sitting on the stack. Those are the arguments. So we have increment D to deallocate those two items that are still sitting on the stack. Cool. Alright, so I have just written a whole bunch of code and have not tested the program yet. Okay, so maybe it's time to test the program. Okay, alright, so to test the program, let's go back to the C code first. Okay, because one thing you can do when you're trying to test your code when it's partially done is to look at the behavior of the code if it was done in C as well. In other words, you want your current code to be doing the same thing as this modified C code because that is your assembly code is basically doing this right now. It has the outer conditional statement, it has the first inner conditional statement, and the action, the then branch of the inner conditional statement. But it doesn't have anything else defined at this point. So you kind of want to make sure that your program would behave the same thing as the C code. The C code is easy to check because you do have GDB as a debugger. You can set up breakpoints, you can examine values of the parameters and whatnot. So you can check the C code's behavior, at least how many times it's going to call itself, when is it going to stop, blah blah blah, etc. etc. And then you can check your assembly code to make sure that it is doing something exactly like that. All right. So that being said, okay, how should we test the C code? Okay. So the first thing I would test, in the C code is really just pass a null pointer because that's something that I said I would test before. Let's go for that at this point. Okay, so I'm gonna Oh, right. So I'm gonna do this in the C code as well. So I really should not be overwriting that code. I should have just commented out the line of code, and so that I don't lose what it is supposed to be. So I'm gonna do the same thing over here, and change this back to the address of A, like so. So this way I don't forget um, how it was supposed to be. Oh, um, not quite sure what I did, but that was not good. Um, it's okay. I think I recovered everything now. Alright, so let's go ahead and test the program right now, and we're going to keep an eye on the C code and the assembly code. So we'll rerun the code. And the reality is, I already wrote too many lines of code at this point already. But at least, it's supposed to be pretty simple because the AND AA is supposed to set the Z flag this time, and therefore it should not perform the condition. There was a label missing an initial underscore. That would have caused an error that the assembler can catch, and it did. Okay, very good. Okay, T then and if one, and then the label is not found here. Okay, so let's fix that first, because when I was, kind of typing away on the keyboard, I think I made a typing mistake somewhere. There we go. So it has an initial score underscore, and it's not matching the reference. Okay, thank you, Paul. I did not even bother to check, and the script actually checked for me, except I didn't read it. See, the script actually checked right here, and it said the source file did not assemble correctly, and I didn't check that and go like, okay, let's still check the trace. That was silly of me. Yes. All right, so let's check again. Okay, so it should have said, object code is good, except last time it said the source file did not assemble correctly. So the guy who wrote the script to check for stuff like that decided to ignore the error messages of his own script. Yeah, I cannot get any dumber than that, I have to admit. All right, so this time it did go through, and let's go through the analysis. And it did check, the Z flag does become 1 because I did pass a null pointer, and as a result, it did not go to the no op instruction because the no op instruction is at this location. I'm just trying to find the no op. Oh, I don't have the no op anymore because it just jumped around the entire thing to the end of the conditional statement. So it really should not have executed any code inside the outer conditional statement, which means the JCI here should have brought us all the way, not this one, the other one. The JCI here should have taken us all the way to the end. So that means we should have jumped from location 17 all the way to location 34. So 17 to 34, and oh, okay, wrong thing to click. All right, so let's check. It did go from 17 to 34, so we did skip over the entire body of the outer conditional statement. So we're good. Okay, so if we pass a null pointer, it knows to do absolutely nothing. Do not do any recursion. So what do we do now? Should we continue to write the program? No, because we still have to check to make sure that when it does do the recursion, it would do it correctly. So we want to give it the address of a node where the L member is indeed a 0, because in that case it should also not do any recursion. So now we go back to the original program, and we want to find a node where the member L is a 0. And there are a few of these. E is definitely like that because E actually has both the R and the L members both being null. So we're going to try E. Okay, so we'll use E in this case, the address of E to be exact, and then we'll do the matching change in the C code and change that over here. So we'll change this 0 to E, and this time it's the label E. It is not register E, which we don't have a register E. Okay, so E has to be a label. All right, save the code. And in reality, if I were doing this, actually, if I were learning this and doing this, I would have tested the C code as well to make sure that the C code would agree and say, we are not doing a recursive call because even though PTR is not null, the member L of the structure the PTR is pointing to is null. So that's why I'm not going to go for the recursion. So I would have tested that in the C code before I even bother to run this in assembly. But once again, we are running out of time, so I'm going to go straight to the assembly code to check that. All right. So now we have to figure out, how can we tell whether the program worked or not correctly? So if it had worked correctly, this JZI should have happened, and we should have skipped all of this code here, which is responsible for the recursive call, and instead we would have ended up here. So now we go to the assembly code or the assemble tab to find out what addresses those lines of code are corresponding. So we should have jumped directly from location 3.4. No, I take it back. We should have jumped from location no, not that, 2.2. Okay, because column W is the address. So we should have jumped from location 2.2 all the way to location 3.4 this time. All right, so we go to analysis, and we can see that we did jump from location 2.2 to location 3.4, so the code is working correctly. So the nested portion of the loop is also working. All right, so let's see whether the recursive call itself is working. So this time, when we check it, you can see that I haven't done a single change in terms of the actual subroutine, but I'm giving it multiple test cases to see whether it is working with all of those test cases. So we're going to give it a test case where the L member of the structure is actually non-null. So I cannot remember which member is which member. I'm going to have to okay, I just did roll back some changes that I was not intending to do. All right, so now we need to go back to the structure, and we can see L is the second member, and then we just have to find a node where the second member is not null, like B. Okay, we could have used A, but the problem with A is pointing to B and then B is pointing to C, so it's going to cause multiple levels of recursion. I want to keep it simple. Okay, so I just want to use C where it would only have one level of recursion, and then once we get to C, it would have a 0 for the L member, and then that should stop the recursion, and then it should go back up again. Okay, so that's what we'll do in the C assembly code as well. So this time we change to the address of B instead of the address of E. I got it saved. That's my other favorite dumb mistake to make, is to make changes and then forgetting to save and then run the code again, only to realize that the code is doing exactly the same as before. So let's go ahead and rerun it. Okay, object code is good, so we didn't make any syntax error. All right, so now we get back to the code. And how should we check it? Okay, because that's always the big question is, I made some changes, I am rerunning the code, but how do I know this code is working correctly or not? So this time we should look for a second invocation, because it is going the recursive call is going to happen. So it's going to call itself again. So that means at location 2.4 it is not branching to location 3.4, and instead it's going to go through some code here. So the way we can tell that it is going through the recursive call, the first sign of the recursive call is we are pushing more things on the stack. Register B, excuse me, register D. Where are you? Right here. So register D was a F2 before, and then somewhere after 2.4, we decremented the stack pointer to F1. So we're pushing something on the stack. We're pushing FF in this case, onto the stack, and then we're pushing 09 on the stack. So now we have to ask, what is FF? FF is supposed to be array, which is a pointer to some character. And it is indeed FF because it is the first. It's one of the local variables in main, and then when we go back to the definition of local variables in main, we should find that it's the one that has the highest address. So this is actually correct. We have the address of the pointer array in main being pushed first, and now we have a 09, which is supposed to be the address of C, because remember B is using its L member to point to C, so this is supposed to be C, or the address of C, and we want to double check that. So now we go back to how C is defined, and it is indeed starting at location 09. So we know it is pushing the right stuff on the stack. And let's see. Oh, I was scrolling in the wrong direction. There we go. So we are pushing the second argument, the first argument. This is the return address. And then when you get here, it should not do any branching. Or I shouldn't say that. It should not do any recursive call because it would go from 2.4 to location 3.4. So it goes to 3.4, and it did not go to location 3.4, and instead it is pushing again. Okay. And it's pushing itself again on the stack. That is not right. Okay. Okay, so I think I know what is going on. I know why it is not working correctly. All right. So at this point, I know the program is not working because I know it is not supposed to call again, recursively. There should be only 2 invocations, and then the program should start to return. So now the question is, why is it deciding to go for another recursive call? And so the test did not set the Z flag here. So we need to go back to the Assemble tab, find out where the and whatever register is located. It's not this one that we're worried about, it is this one here. It is at location 1D. So we want to look at the trace at location 1D. What was the result? So here's 1D and the Z flag. So we have B, register B being 09, and it is supposed to be 00. So to make sure that really should be the case, we can look at the source code. So in the source code, and we go back to the definition of B. No, we are looking at C. So let's go back to the Assemble tab, and let's find out where C is defined. So C is defined at location 9. It should have the L member being 0 and 0. And instead, we are not getting that. Alright, so let's back up in the trace analysis. And we're going to go back up to what is being pushed on the stack. So we pushed 0C on the stack. This is the second argument. This is the first argument. And 0C is, let's see, whose address is that? So 0C is the address of B. So it is passing the address of itself on the stack. All right. And let me check in main whether we are using the address of B or not. So we are indeed using the address of B. So that means when we are pushing the second argument on the stack in the recursive call, it is pushing the wrong thing on the stack. So we'll go check that. Let me point out this is pushing the second argument. Oops. There we go. This is pushing the second argument. It's the first argument that is wrong, which is this B here. So we should look at what B has at this point. So B is the offset to the node, and we add A to B. A is the pointer, which is the base address of the entire structure. So after this, B should have the address of the member L. And BB does not change the value of B, so whatever B was would still be the same. And this is getting the value of the L member instead of the address of the L member. And then from there to here, I did not modify B at all. Okay. Let's go back to, then we backtrace the code. Okay, so we go to the analysis tab and then we backtrace it a little bit more. So let's see. So we want to look in column D to find out, what put a value into register B, because whatever is in register B is what we are pushing in this instruction here. So register B got C. This is where we do the AND BB. This is where we did the LD BB. And this is where we finished the calculation of where member L of where PTR is pointing to is at this point. So we want to check the address 10 and see what it is. So location 10 is right here. It is indeed, it is using structure A and not structure B. Because if I was using structure B, it should have a 0D instead of a 10 in it. Nope. Okay. So I am confusing myself big time because this is actually the wrong trace. This is the wrong trace because it says private assembler. Okay, I should. Okay, another user operator error here. Okay, I have been looking at the wrong analysis. It is supposed to be this one. Okay. All right, so right. So I need to go back and check again and see whether this one terminates, because if it were pushing the wrong item on the stack, it would have gone into an infinite recursion. And it did not get into infinite recursion, so that means I probably was chasing the wrong end in myself. Okay, so let's double check this. It is pushing 09, and I'm looking for 2-4 jumping to 3-4. It did go from 2-4 to 2-2 to 3-4, and the assemble tab at location 2-2 is the JZI, and then at location 3-4 is the label where we're supposed to branch to. This is location 3-4. Okay, so that part is correct. All right, so totally my bad, because I was using the wrong tab up here. Instead of jumping between these two tabs in the same spreadsheet, I was using a different sheet to begin with. Okay. All right, so the program did work correctly up to this point. So that is good because it means the approach is working with the nested conditional statement. So I am going to do the other nested conditional statement first before I go back to implement the nastiest part of the subroutine, because the second part is really kind of the same as the first one, except I cannot rely on register B to contain PTR points to R anymore, but I'm going to have to test it anyway. So, we can use the same structure of code um, over there. All right, so knowing that this is what we want to do at this point, let's find out, what we can use here, and what kind of, we have to be careful when we do this too. All right, so starting on, okay, I'm going to put on the line numbers. Starting on line 48 and ending at line 47 is how we did the first nested conditional statement. And we're going to do about the same thing with the second one. So in VI, I can just say line 48 to line 75, copy to here. So now we have two copies. Now, copy and paste is nice, but you have to be very careful because you kind of have to make sure that you make all the changes that you need to make um, after you make the copy. So this time we are accessing member R, and the conditional branch also has to branch the wrong to the right label. So the reference has to change. The definition also has to change. The rest of the code can remain the same because I'm still relying on the fact that we have member R, the value of member R of the structure the PTR is pointing to, and it's still in register B because the structure of the code is indeed the same. All right, so given that is the code, now we want to find out, what should we use to test this code? So we can test something that has no, so where the member R is a 0 and member L is also 0, which is E. So now we can go to the main of this code, and once again we pick E up, okay, right here. And it should only have one single invocation of the subroutine because both the L and the R members are zeros in this case. So both nested conditional statement should not go for the recursive call. Okay, so we'll make sure that we save the file and then retest it. There we go. All right. All right, so I'm going to ask you guys, how can I double check that there's only one single recursion this time and not like multiple recursion? What is the quickest way to confirm that we only called traverse exactly once? I'll let you guys think about it a little bit because it is a question that you should be able to answer. So once again, the question is, how do we make sure that traverse is called only once during the execution of this program? You could check the stack to make sure that it does not go below where we expect it with only one single invocation. That's one thing you can check, but that's an easier way to check. All right, so that will work too, but I'm going to tell you the shortcut to do this. The shortcut to do this is to find the entry point of traverse. So the entry point of traverse is right here. It is at location 1, 2. We should get to location 1, 2 exactly once in this particular trace. That is the easiest way to check that we only called traverse exactly once. All right, so let's find out. Okay, so we do a Control H, which will give us this menu. We type 1, 2. It's already limiting the search range to column A, so that's all good. We click Find. We find 1, which is on row 41. And then when we click Find again, it will say no more results found, looping around. So that is how we can confirm that we only called traverse exactly once in this code. And it doesn't involve the analysis of the stack either. So, I mean, the other way is not wrong. This one is just easier. Okay. So that's good. Okay, so that means the conditional statement seems to be working. So the next test case I'm going to throw at this program is the case when we have exactly one single instance of recursion. So this time we're looking at R, and R should not be a null. So if I use the address of D in main when we called traverse, that should have we should end up with exactly two invocations of traverse. So we will change the address of E to the address of D, save the code, run it again. And this time we're going to use the same trick, just do a control H on column A and look for 1, 2. So now we go back to the trace, highlight column A, control H, look for location 1, 2. And we find the first one on row 41, just like last time. That is correct. And we should find one more on row 101. And if we click find again, it should not find a third one. It should go back to the first one and go like, nope, we cannot find anything. We're looping back. So there we go. It did loop back. All right, so this is good, okay, because this is comforting because I can now be fairly sure that the recursive stuff is working okay. It's just that the program doesn't do the other two statements that are that's kind of the most important part of the whole algorithm, are those two in between. But at least the control structure itself is working. If I was using revision control, I would have put one into the revision control system so that I can basically leave behind a comment and go like, this program, the control structure is all working. Now I'm going to work on the part that is in the middle that looks kind of nasty. Okay. All right. So we're going to go back to the C code to reflect what we are about to do. Get rid of these two. So put these two lines of code back into the program. And those two lines of code are between the two conditional statements. So that means it belongs here. Okay, this is right between the two conditional statements. And in order to remind myself what I'm supposed to be doing, I can always just kind of repeat the C code here. And the other one is whatever array is pointing to is going to increment by 1. Okay, so I changed the syntax a little bit, but it means exactly the same thing. All right, so when I'm doing this part, I'm just going to do it the usual way. Okay, I'm not going to take any shortcut or try to optimize anything. So we'll do the LDI a t underscore ptr add ad. And in order for the pointer to be pointing to something, I need the value of the parameter. So we have a LDA a, and then we need to we want to access a certain member of the structure that is now pointed to by register A. So we're going to put the offset into a different register, say register B. Oh, this is node underscore value. And then we add those two. I don't think I need PTR anymore, so either way is fine. Add BA in this case. So register A now has the address of member value of the structure that PTR is pointing to, and we are not interested in the address of member value. We are interested in the value of member value. So now we need an LDAA, like so. So that should be the right hand side. The left hand side looks really nasty because of the double asterisk. Well, you just have to kind of track it, how many times you need to dereference, okay? Because and once again, I'm not putting comments or extensive comment into this program because I want you to do it. Now, in the end, I really have no idea whether people are taking my recommendations or not, whether they're actually putting comments into these programs or not. But in the end, it is also not my business, okay? Because if some people say I can keep track of all of this stuff in my head, who am I to say that those people really need to spend the time to type all of this stuff? So you kind of have to evaluate for yourself, whether my recommendation is going to be helpful to you or not. All right. So enough nagging. moving on with the coding. So now we have t underscore array into b. That's the offset. Add bd. That's the address of array. So now we have ampersand array basically in register B, which is not what we want. So we have a LDBB. Now we have array itself, and then we have another LDBB. Now we have asterisk array. Now we need to think. But we need one more dereference because we are supposed to have asterisk asterisk array, and register B only has asterisk array. But remember what we are doing to the left-hand side. We are supposed to be storing. So if I do another LDBB, I'll be getting the value of double asterisk array. But that's not what assignment is doing. Assignment wants to change that location. So the next dereference is going to be st because we want to store to where register B is pointing to. Register B is indeed asterisk array, but we want to store to what asterisk array is pointing to, and that's why we have a st instruction. And register A has the right hand side, so we just do a stba like that. Oh, okay. I just got a private text, but I cannot respond to it because I'm in a class. So I'm gonna skip that for now. Alright, so I think that I have just accomplished this statement here. I'm gonna test the program because this one is kind of tricky, right? Because how many times should I dereference and blah blah blah. So I'm gonna test the program right now. But also remember, when you test your program, you need to know what your program is supposed to do. So I'm just gonna make sure that my C code is mirroring, the assembly code, or the two at least are consistent. So this is where you kind of need to read the C code and find out, okay, how should I test the C code as it is right now without the increment of whatever array is pointing to. So what should you do? Well, first of all, passing a null pointer is not going to be helpful because if you pass a null pointer, it's going to skip all of this stuff here. But you can pass something that has both the L and the R members both being null, because we are not trying to check whether it's recursion, whether it's doing both of these recursions correctly or not. We just want to see whether this is executed correctly or not. Indeed, it is now helpful to choose E or C to do this because we are supposed to be storing the value, which is 200 in this case, to whatever array is pointing to, and it should only do it once, so there's no danger of having that location overwritten again. So both E and C would make very good test cases for the program as it is right now. But then what is array? Okay, so now we need to look at main and find out what we are passing as quote-unquote array. We are passing the address of ptr in main, and ptr is initialized to be at the beginning of buffer. So that means all we are doing is we are writing 1 byte to the first byte of the array buffer, which is a local variable of main. That's all we are doing. Okay. Now we need to go back to the assembly code and basically check out where buffer is supposed to be. So buffer is supposed to be pointed to by the stack pointer once everything is allocated. So when you think about what the stack should look like, buffer is all the way at the bottom here. So buffer has 10 elements in it. So we got buffer 1, buffer 2. Okay, I'm getting a little lazy here. So we got 3, 4, 5. So this is 5, 4, 3, and we need 4 more of these things. So we got 9, 8, 7, 6. There we go. And then PTR is right after. How do I know? Because that's how PTR is defined here. So we know that PTR is indeed at location 255. So if this is location 255, This is 254 3 2 1 0 9 8 7 6 5. So this is supposed to be at location 245. So now when we change the program so that the first argument is, let's pick E in this case, that means location 245 should be overwritten with whatever hexadecimal representation it is for 200. Okay, that is how we check whether the program works or not. So now we go back to the script. So there's a lot of analysis going in to find out, what the program is supposed to do based on the code that we have at this point. Okay, that is really, really important when you are debugging code, and not just in assembly either. Okay. All right, so let's go check out column C this time, because column C reflects, all the right operations to RAM, and we already know that we want to check for overwriting location 245, but 245 is in decimal, so we want to find out what it is like in hexadecimal. In hexadecimal, we are basically just subtracting 10 from FF. So FF minus 0A is going to be F5. So we should be looking at asterisk F5 equals to something, okay? And whatever that something is should be representing 200. But this time we have to be careful, because I think, oh, okay, the way it is right now is fine, because it's not using regular expression, because in regular expression the symbol asterisk has a special meaning, so we have to be careful with that. Okay, so click find, and it is claiming that we are writing C8 in hexadecimal into that location. So now the big question is C8 200? That's the question. So we are basically asking, is 12 times 16, because C is 12, so, and that particular digit represents the quantity of 16s, which is 16 to the power of 1. I hope you still remember your base conversion. So 12 times 16 is 192, and then plus 8 is indeed 200. Okay, very good. Are we overwriting that location again? Because we are not supposed to be overwriting that location again. So we click find again, and we do not find any additional overwriting of that location. So this is how we can check to make sure that, okay, I have to go back to the right line of code here. So this is how we can check that this line of code in C is now indeed implemented correctly in assembly code, which is right here. Okay, so now that we have verified that this line of code is implemented correctly, then we can just go ahead and implement the next one. Alright, so the next one, I'm going to start it from scratch again. So we are not going to reuse any register from before, even though in this case we could have saved something from the previous statement and reuse it, because we did compute okay, so let's check what register B has. Offset, address of array, this is asterisk array. So we only want to so we have both the value and also the address of what we need. Let me just do a poll. Do you guys want to look at the optimized version of this code, or do you want me to go for the unoptimized version of this code? Because the optimized version of this code is going to be quite a bit simpler compared to the unoptimized version. So I'll let you guys, decide how you want me to proceed. Optimized. Very good. Okay. So when we are looking at the optimized version, then we need to refer to the value of what array is pointing to. So let's find out which B has that. Okay, so we have, once again, offset, the address of array. This is array. This is asterisk array. So this B, which is still preserved because ST does not change register B. So register B has, okay, so I'm going to say register B has whatever array is pointing to. But when we use asterisk array on the left hand side, we cannot use that B, right? Because B is representing the value, which is, well, okay, we have to remember to plus 1. So we'll just say, increment B. So now B is whatever array is pointing to plus 1. So now we need to store it back into what array is pointing to, which means we need a register to be just array and not array asterisk. So once again, offset, address of array, and this is array. So that means at this point, I might want to do a CPR right after that. So I'm going to do a CPR, okay, just saving the value of register B to register C. And now I can reuse register C and go like, yeah, let's store that again. So we'll store into wherever register C is pointing to the value of B, which is incremented already at this point. Alright, so I'm going to pause a little bit here just so that you guys have some time to digest, what I have done. So basically, register B after this LD instruction has the content of whatever array is pointing to, and the register B right after this LD instruction has array in it. Okay, in other words, it just has the parameter array in register B after this LD instruction. So the CPR is making a copy of that, and someone may say, but that I heard that this is not a good idea, using a register to make a copy of something. Well, it's not a good idea if I have, a function call in between, but since I do not have a function call in between, I can count on these registers having the value that they are loaded with. Okay, it's just that whenever we have a function call, you can kiss registers A, B, and C goodbye because there's no guarantee that the subroutine would preserve the value of those registers. But since I'm not calling any other subroutine right now, it's okay, not a problem. All right. Okay, so let's just say that this is what we are doing, and we want to see if this program works correctly or not. And we're going to keep the same thing. So I'm going to go back to the C code and change it so that we uncomment the line of code that we think we have just implemented. So in the code here, I'm going to keep using E as the structure. So we would increment whatever array is pointing to by 1. But whatever array is pointing to by 1, whatever array is pointing to is really just the local variable PTR of main, which is at location FF. So we should see the content of location FF to be written twice in this case. The first time it's written is because we did the initialization in main, and then the second time it is going to be incremented because of the statement in traverse. So that is what we should be looking for when we debug the program. Alright, so let's go ahead and test the code. And then we go to the trace, and let me get out of this one first. Alright, so we are now looking for write operations to location FF. And as I said, there should be two events. The first event is the initialization in main, and then the second one is the increment inside traverse. So let's go ahead and check for that. So we are looking for asterisk FF equals to, because that represents the overwriting of location FF in RAM. And double check the column is indeed column C. Okay, that's all good. So click on find. This is the first time. And we recognize F5 because that is where buffer is located on the stack. So this is the initialization inside main. And let's find again. Uh-oh, it is not incrementing again. Okay. So, okay, so the program does not seem to be working, which is fine. Okay, because now we need to debug the program. So once again, if the program is not working, I'm going to use this opportunity to teach you guys how to debug a program. Uh, right, right. Okay. Yep. I'm just being okay. Now that I have saved the file, let's try again. It doesn't mean the program will still work correctly. Okay, it's just that before I save the program, it's definitely not going to work the same way. Yeah, programming step 0. Somebody has to keep telling tech, save the code first, save the code first. All right, so let's do this one more time. Okay, not control F, it's control H. So control F does something else. Okay, control H, asterisk FF equals 2, and find. There we go. This is the first one. And there we go, the second one. Whew. Okay, so it does work correctly this time. Yay! Thank you guys. Yeah, thank you, Fooling, for reminding me that I did not save the code before running it again. Yeah, I'm just I'm staring into outer space because in my mind I'm already thinking about, okay, is there a tool that I can use to see if I have made changes in the file that I'm submitting in submit? And the answer is yes. There's actually a way to check it because in VI, whenever I do editing, it would actually change there's a hidden file starting with a dot that it would change. So the date stamp or the timestamp of that swap file, it's called a swap file, by the way. So the swap file date stamp is going to change if I have made changes in the editor, but it has not saved. So the file itself and its swap file will have different timestamps, and the submit program, knowing what text file I'm sending over to the assembler, can automatically assume that I'm using VI to edit the file, check the timestamp of the swap file. If the swap file timestamp is different from the actual text file, my script can actually just give me a message and go like, tag, you forgot to save your file again. Yes, engineering in action. Well, I need all the engineering, possible to counter my own stupidness, own stupidity. There we go. Stupidity, not stupidness. There's no such word as stupidness. It is called stupidity. Well, what can I say? What can I say? Embarrassing moments. All right. So I think this program is done. Okay. So if I think this program is done, we will change the program all the way back to the original parameter, which is LDIAA. So I'm going to uncomment the code that it is supposed to be and then delete the test code, and we'll make a matching change in the C code like so. Okay, so if you have tested the C code, you kind of know what we should find in buffer, and we're gonna test it now. Okay, so double check, make sure it's safe first. Yep, it is. All right, there we go. All right, so now we are going to check what is being put into buffer. Um, Now we can always run the C code again, just to know what we're supposed to be seeing in buffer. So that's what we'll do first. So gcc-g-o tree.c. Oh, okay. Oh, wrong folder, wrong folder. Okay, push D to temp new tree. There we go. Now repeat that command. It should work now. There we go. So gdb tree, and put a breakpoint on line 39. Just run the program at full speed, and we want to find out what is in buffer. Alright, so I have explained this before. \001 is in octo, just one, it's octo 001, which is really just the value of 1. This is the value of 2. \n itself is basically what we know as 10, because 10 is the ASCII code of the line feed character, which is represented as \n. The ASCII code of D is, oh, I cannot remember. Let's find out. 100. Thank you. So the letter D is representing the value, the unsigned value of 100 in base 10, and then \310 should be our 200, okay? Because it's 3 times 64 times 8, plus 8, sorry. 3 times 64 is 192, 192 plus 8 is 200. So we are basically getting the value 1, 2, 10, 100, and 200 into buffer. So now the question is, are we finding those items in the case of the trace? So we know the first, oh, okay, I was using the wrong function key. So let me get out of here. All right, so what I'm going to do now is I'm going to show you guys, the power of regular expression. Okay, because my mind just branched out, right when I said the power of, because I just watched He-Man and Masters of the Universe yesterday. So that's why my brain just go like, hey, that reminds me of something that is kind of cool, but it's not related to the class. All right, so this time I'm going to use regular expression. So in regular expression, the asterisk symbol needs to be escaped with a backslash. And then we have f, which is supposed to be found. And now we can use a range of digits, starting with 5, because 5 is f5 is corresponding to the address of buffer bracket 0. So we're going to check 5 locations. So that would be 5, 6, 7, 8, 9, like so, and then close the bracket. I'm hoping some of you look at this and go like, yeah, I remember that when we talked about base 10 scientific notation, we kind of talked about regular expression a little bit. That is why regular expression is useful, because now I can have one single search pattern and it will locate, hopefully all 5 updates to those locations in RAM. But we do have to specify that we are using regular expression in this case. And that should be it. Okay. All right. Let's go ahead and see what this is going to do. So location, this is the first location. This is corresponding to buffer bracket 0 is indeed 1. And then we find 2. And then we find 10, which is 0.8 in hexadecimal. And then we find 64, which is 100, in hexadecimal, because 6 times 16 is 96. 96 plus 4 is 100. And finally, we have C8, which is 12 times 16, which is 192, plus 8 is indeed 200. So we have just confirmed that the C code and the assembly code agree in terms of what they are doing. So, not really surprisingly, this took up almost the entire class, which means tomorrow I'm going to spend most of that time to talk about the practice exam. The practice exam is already an attachment from yesterday's text channel. I could just do a recording of that so that you guys can review the key to the exam questions, so that in the lecture you guys can actually ask me questions based on the practice question itself, and also based on the key that I'm going to provide and the explanation. So that way, if my recorded explanation is not explaining certain things clearly, then we can use the class time for interactive synchronous clarification. I think that's probably a good idea. Yeah, I can see you guys like that too. It does mean that you guys will have to spend some more time, on your own, other than, outside of class time, to kind of watch the video and also work on the exam question itself. But I think that's going to be beneficial. That would be the best use of our time. Okay, sounds good. So I'm going to do that. There's no lab tonight, but I'll be online. I'll probably just working on the um, explanation of the answer to the practice question. So I'll be online for another 80 minutes because I'm obligated, to basically be here during those 80 minutes. So if you have any questions related to these topics, it'll be good to ask. And I lied because I said I would be able to give you guys the raw score. I didn't quite get around to do it, but I think I found a better way to do it rather than just responding to individually and also to kind of hand enter everything. So I think I can go ahead and upload all the PDFs because I hand graded. Okay, I actually use handwriting to hand grade every single one of exam 2. So I can upload all of those PDFs and then send the PDF to the person with the ID. So I think I can write a script to do that in Google Drive. It will take me some time, but it will be done. So that way I have a systematic way to do something that otherwise would be a lot of chore. So that's what I'll be doing for the next 80 minutes or so. If you have any questions, use the text channel to ask. And I am going to